We have seen that urn models are frequently useful in modeling complex phenomena. Let's start with a plain, rather banal problem. Trite, I don't have any particular application in mind other than of an illustration of calculations involving the binomial. So here is an urn problem. Suppose n balls are randomly distributed into r urns. We think of the first n as distinguished and we ask, what is the chance that there are exactly k balls in the first n? What is the chance that the first two urns between them get k balls? Pause for a moment, see if you can set up the problem and write it down. And when you're ready, resume the lecture. Now that you're back, it's clear that I have in mind a relation between this urn problem and a coin tossing problem. And the metaphor is going to be fairly clear. Suppose S represents the number of balls in the first urn, and let T represent the number of balls in the first two urns. They are, of course, chance variables, and I'd like to say something about both S and T. And what can I say about it? Let's think about the first urn. There are n balls, and each ball has got a probability 1 over r of being placed in the first urn. There are exactly r possibilities, and so the chance is 1 over r that you go into one of them. The balls are placed in urns independently of each other. If we define success as a ball is placed into the first urn, then what we're really doing is tossing a coin whose success probability is 1 over r, and we toss this n times, 1 for each of the balls. And therefore, the number of balls that end up in the first urn is governed by the accumulated number of successes in these n tosses. In other words, it's going to be governed by a binomial distribution corresponding to n trials, 1 for each of the balls, whose success probability is 1 over r of landing in the first urn. What about the first two urns put together? Well, this is just a small variation on that theme. If you imagine the first two urns together as forming a block, the chance of any ball falling into the first or the second urn is 2 in r. There are 2 out of the r possibilities that it could land into. We now have a succession of n Bernoulli trials where the success probability now is 2 over r. And therefore, T, the number of balls in the first two urns, is governed by a binomial distribution corresponding to n trials, and where the success probability P now is now 2 over r. And with this in hand, we can now simply write down our problems. The probability that the first urn sees exactly k balls is governed by the binomial probability corresponding to n trials, k successes, and where the success probability is 1 over r. And we just write it down. The probability that the first two urns see k balls is governed exactly by the binomial probability corresponding to n trials, a success probability p of 2 over r, and exactly k successes. And there we have it.